Let's start off. Let's look at some of the basic things about our periodic table. Some of the basic things we know is that the atomic number will always tell me the protons. They are positive. So these are in the nucleus. Remember, these are one of the three subatomic particles. Subatomic just means smaller than an atom. So the only thing that's smaller than an atom are the things that make up that atom. And so a proton just happens to be one of those things. Now, a proton is the equivalent of 1 AMU, which means 1 atomic mass unit. So for every proton that's in the nucleus, that adds 1 more AMU to the weight or mass of that atom. Now, because we know all the atoms in the periodic table are neutral, then it must have an equal number of negative things to balance it. So this 14 for silicon, for example, tells me that silicon also has 14 electrons, which are negative. So that balances it. It makes it a neutral atom. Now, to find the neutrons, remember the atomic mass is a weight of the nucleus, how much that nucleus weighs, because the electrons are too small to even consider for weight. So this total number, remember it's got a decimal point because it also includes an average of the isotopes, which are the uncommon forms of that atom that have extra or fewer neutrons than the normal atom. So we have to round this number. So when we look at that, I believe that this is like 28. It's kind of hard to tell. It's kind of fuzzy. But anyway, let's assume it's 28.0 something. So we would say 28 minus 14, because we know that 14 tells me protons. So if this 28 tells me a total of protons and neutrons, when I subtract the proton value and I'm left with 14, then that tells me that's the number of neutrons. Now, each neutron is also the size of a proton, so every neutron is the equivalent of 1 AMU. So it has an atomic mass unit of 1. So that's why if you have 14 protons and 14 neutrons, when you add them together you get 28. That is a 28 AMU. So silicon has an atomic mass unit of 28. Now let's look at some other things. We realize that a group and family mean the same thing. This is group 1, this is group 2, and so on. It goes all the way across to group 18. Now, one thing that's important to understand is the atoms on this side of the periodic table are very reactive because they have a fewer number of electrons in their outer energy shell. If you forget what that is, look back at a previous lesson or continue to watch this video. We'll talk a little more about that. But anyway, as we go across the periodic table, we go from very reactive or very unstable to very stable. And the reason that is we move across the table, we are adding an electron to that outer ring every time we move across. Now, we have to ignore the rule with these atoms right here. These are the transition metals. These transition metals do not follow the same rule for finding valence electrons, okay? But we can say with certainty that everything in group 1 has 1 valence electron, everything in group 2 has 2, everything in group 13 has 3, group 14 has 4, group 15 has 5, group 16 has 6, group 17 has 7, and group 18 has 8 valence electrons. So they have a full outer electron ring in group 18. Now there is one exception. Helium, of course, is in period 1, which tells me it has 1 energy ring. Well, if you remember our rule, 2 and 8 tells us that the first ring can hold 2 electrons, the second rings or the second, third, and fourth rings and so on can hold up to 8. And so they want to get that stability. They want a full outer ring. Well, in group 18, they all have a full outer ring. They have achieved what every atom wants, and that's stability, because their energy level is full in that outer ring. Okay, so these atoms in group 18 are completely stable. They're called the noble gases. Okay, now back to what we just said. Period 1, period 2, period 3, 4, 5, 6, and 7. Those period numbers tell me how many rings will be around that nucleus. Okay, so that will make more sense here in just a minute as we move on. Now remember, everything to the left-hand side of this zigzag line are metals. Everything to the right of the zigzag line are non-metals. And remember, metal properties are that they can conduct heat and electricity. They're malleable, which means they can be smashed flat. They're ductile, which means they can be spooled into a wire. And the fourth one is that they have luster. They shine when light hits them. Now, nonmetals, on the other hand, are quite the opposite. They don't conduct heat and electricity. They make good insulators. Many of them are gases. So those particular things don't qualify for the nonmetals. Now, these atoms here that I'm putting stripes on, remember, they are the metalloids. They have properties of metals and nonmetals. And so some of them may conduct heat and electricity, some of them may not, some of them may have luster, some may not. Now, aluminum, of course, is a metal. Even though he's touching the line, he's the one that kind of falls into the metal category. So he's not a metalloid. Okay, so let's move on to something else. Okay, if I look, this is boron. Let's look back where boron is located. Let's go back here. Boron, and I'm going to clear this board for just a second so we can see it better. So boron is right here, and boron is in group 13, so that's important. So he's in group 13, period 2. Okay? So period 2, group 13, that's important to remember. So when we go back, boron is in group 13, so I'm going to put group 13, period 2. What that tells me is he has 2 energy rings, so we really don't count this ring. This is a nucleus. 1 ring, 2 rings. So this ring doesn't really count for boron. He doesn't have a 3rd ring. Now he is in group 13, which tells me some things about him. That tells me he has 3 electrons in his outer ring. So let's go ahead and build boron. Well, this 5, the atomic number, remember, tells me protons. So this atom has 5 protons. 1, 2, 3, 4, 5 protons, okay? Well, if he has 5 protons, he needs an equal number of electrons to balance it. So remember, the first ring can hold 2. So we'll put 2 electrons right here. The next ring can hold up to 8. But hang on just a second. He doesn't have a total of 10, does he? If we look, he has a total of 5. So 1, 2, I need just a few more electrons to make him happy or to satisfy who he is. So he needs 5 more. So 5 minus 2 is 3. So he needs 3 more. So I'm going to put 1, 2, 3. Now how do I find the neutrons? Remember, I have to round this number, 10.81, because that is a total of his protons and neutrons. So that rounds to 11. 11 minus 5 is 6. So he has 6 neutrons. So I'm going to add 6 neutrons to his nucleus. 1, 2, 3, 4, 5, 6. Now when we look at the weight of that atom, if we total these up in the nucleus, that's his weight. If we add the 5 protons he had plus the 6 neutrons he had, his weight is 11. So why is it 10.81? Because there might be other atoms of boron that are isotopes that have fewer numbers of electrons or fewer numbers of neutrons. So those uncommon forms or isotopes just happen to make the average of it a little bit less than 11. Okay, so let's do the same thing with these other choices here, or this other atom here. So let me erase all this, and we'll start over. Okay, so let's look at sodium. Sodium is our next atom on this list. So I want to go back and look again at our periodic table. And sodium right over here is in group 1, period 3. So that period 3 tells me he has 3 energy rings. Group 1 tells me he has 1 electron in the outer ring. So let's look at that. Okay, so remember he was in group 1, period 3. Okay, so let's see, we got 1, 2, 3 rings. We need all 3 of them for sodium. He's in group 1, which means he has 1 electron in that outer ring. So I'm going to just see if that works. I'm going to just place him out there and see if when we start building this atom, if that holds true. Okay, so remember the 11 tells me protons, so I'm going to put 11 protons in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, bigger atom than boron, obviously, right? It's heavier. It's got more stuff in it. Okay, well, because he has 11 protons, right, that are positive, he needs 11 electrons to balance him. So remember, the first ring can hold 2, so 1, 2. The next ring can hold 8 because of our rule of 2 and 8. So I'm going to put them kind of close together so we can see them. 2, 4, 6, 8. So right now with this ring, I have 8 here, 2 here, that makes 10. That's 11, 11. So see, our rule works. We knew we were going to end up with 3 rings with 1 electron on that outer ring. Okay? We also have to count for the neutrons though. So we have 22.9. So 22.9 rounds to 23. Minus 11. Okay, 3 minus 1 is 2. 2 minus 1 is 1. So he's got 12 neutrons. So I got to add that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I add those 12 black neutrons plus the 11 red protons, then I get an AMU of 23. Okay? Why is it not 23 here? Again, because of those isotopes. There are also uncommon forms of sodium that have different numbers of neutrons that make the atom weigh more or less. So we average that count into their weight, and we get the total weight for sodium in the entire universe, basically what's available out there that has the same protons and electrons as sodium. Okay? Okay, so look at the isotope video if you have trouble. So let's look at how ions are formed real quick. Okay? Let's go back to sodium for just a second. Remember, sodium had this one electron right here in the outer ring. So I'm going to go ahead and do that real quick. I'm just going to pay attention to those electrons. So here's sodium with that one electron in the outer ring. He would love to have 8. That's why he's in group 1. He's very unstable. He wants to get rid of this guy. If he gets rid of him, then it's like he has these 8 electrons just waiting to be on the outside. So if that electron were given away on the outside ring, then it's almost like that ring disappears, and then he's left with this inner ring right here. So if this guy can go away, then it's like this ring becomes this new outside. Okay? So that's what he wants to do. So let's take a look at chlorine for a second. Chlorine is way over here in group 17. So remember what that tells me? That tells me that chlorine has 7 valence electrons. Okay? So that's really important. So let's go back and let's put 7 electrons on this outer ring. 1, oops, he moved kind of where I didn't want him. So 1, 2, 3, 4, 5, 6, 7. So where did I get 7? Remember, he was in group 17 right here. Okay? How do I get this 1 electron? Well, sodium was in group 1. Okay? Well, look at that. Remember our rule of 2 and 8? Let's see what's going on. Okay, sodium right here. Remember, this is sodium, Na, and this is chlorine, Cl. Okay? Notice chlorine is bigger because he's got more stuff. Okay? If we were to add up his protons, he has 17. This one has 11 protons, so he's a smaller atom. But let's see what's going on here. What would happen if this electron magically moved over here? Well, that's interesting. Let's see what would happen. His protons never changed. Remember, he had 17 protons in his nucleus. Right there, that tells me that. This one has 11 protons in its nucleus. Okay? Well, what just happened? Well, he gave away an electron, so now he has 1, 2, 3, 4, 5, 6, 7, 8. Oh, we can't forget about these guys. Let's put them in there too. We got 2 in this other ring. So now he's got 10 electrons. So 11 minus 10 equals 1. Well, that means he's got 1 extra proton in his nucleus. So what that means is he has a +1 charge. So this becomes a cation. But the opposite held true with chlorine over here. Chlorine has all these electrons that we didn't put in, so he's got, whoops, hang on a minute. Fix that. Okay, so he's got 1, 2, 3, 4, 5, 6. Oh, I'm moving them in the wrong spot, aren't I? There we go. Right there. Right here. So there's 8 there. There's 2 on this first ring right here. So when we look at that, he had 17 electrons that balanced his protons, but now we took 1 away. Remember, this one came from over here. It's moved over. So now he's got 18 electrons that are minus. When we subtract the 18 from the 17, we're going to end up with a 1. Well, because he has extra electrons, he's a -1. So he becomes an anion. So remember, opposites attract. Now these two guys are kind of held together for life. They create an ionic bond, which is a really strong bond that now makes table salt. Okay? So group 1 atoms love to bind up with group 17, because when they do that, then they become ionic bonds that share their electrons or give them away. Okay? That's all I have time for, guys. I really encourage you to look at the old videos and really study that hard, okay? Because I really want y'all to be successful. If you have any questions, see me in class, and I hope you all did well on your 6 weeks test.